Hi, I would like to present our paper Dumpling, which is about fine-grained differential JavaScript engine fuzzing. To find bugs in a JavaScript engine, let's first look at what happens if a snippet of JavaScript gets executed by V8, the JavaScript engine running in all Chromium-based browsers. This snippet of JavaScript may be passed back and forth through these four so-called execution tiers. There is Ignition, the interpreter, and Sparkplug, Marklif, and Turbofan, which are just-in-time JIT compilers, which differ in the amount of optimization and speculation they do. The interesting observation from a security point of view is that these four execution tiers must implement JavaScript execution semantics in the exact same way, meaning that even a very small discrepancy, such as a value in Ignition being the float value minus 0.0 and the same value in Turbofan being plus 0.0, can be enough for remote code execution in the JavaScript engine, as shown by this real bug. And our approach wants to compare these execution tiers at runtime and spot such subtle differentials. A very central data structure for our approach is the VM state, which the interpreter operates on when a snippet of JavaScript arrives at the browser. It will be first translated to a very simple bytecode language shown here. That is just register-based bytecode language, and it has a very direct correspondence of the registers. Here, a bunch of information about the function, a copy of global state, and a program counter. The important aspect of the VM state is that it's enough to resume JavaScript, to resume correct JavaScript execution of any program at any point. And as I mentioned, there is JIT compilation, which takes the bytecode, translates it through various intermediate representations and applying all kinds of optimization, translates it to native machine code. And our approach compares VM states from unoptimized execution to an optimized execution of the same program. As an overview of what we do in our paper, we collect traces from the execution of the same program, first optimized and unoptimized, and even during JIT code execution. Then we match these VM state traces together and compare them to find such differentials. With this, we obtain a differential bug oracle that we can integrate into a JavaScript engine fuzzer, such as Fuzzly, which we did in our paper. Fuzzly is a very good, very well-maintained JavaScript engine fuzzer with an extensive grammar and way to generate interesting JavaScript. And with this, we find 8 new bugs in the otherwise well-tested, researched, and fuzzed V8 JavaScript engine. So let's talk about how we do the state extraction, especially during JIT. In JIT, the state is spread across the stack and machine registers, and it's not obvious how can we get back something that is comparable to an interpreter-only execution, and where is the state extraction even possible? Furthermore, in our approach, we do not influence JavaScript execution semantics in any way, meaning that we are especially also not modifying the JavaScript input program in any way. And we also don't modify any JIT compiler optimizations or disable any of those. Our approach ends up using the optimization points, which I will briefly explain. So if function f was JIT compiled with some assumptions over the types and values of the inputs, then the JIT compiler can't be sure that these assumptions are true forever. So it needs to insert checks that, for example, here, a 1 is still an object because it f might be called with a primitive value instead. And these checks are the so-called optimization points, de-optimization points, sorry. Where if the check would fail, the JIT compiler tracks enough context to restore the VM state at this point of the execution and go back to unoptimized execution to continue there. So with this, the de-optimization points are a natural probing position for interesting state that we want to extract. How we do this is we insert just one more assembly instruction there, which is a call to our dumpling hook, and it gets executed in the case where the de-optimization point didn't get hit. So, and in our dumpling hook, we save the machine state, so push all the registers and things, and then we do what the optimization would have done basically in the blue case, up to a point, which means we first build the we build the VM state, which rematerializes escaped values, and then we dump the state, hence the dumpling. So we save it, or I think we like print out the serialized form of the VM state, and then we jump back, like we restore the state saved in 1 and jump back to this exact position where we left off. So we make partial use of the existing de-optimization mechanism to obtain the VM state during JIT execution. Just as a little fun fact, you might have wondered, how do we know like from which de-optimization point we came? For a bunch of technical reasons, we do this by implementing like a embedded disassembler during runtime, which basically finds out where we jumped to it. And yeah, the text here says embedded disassembler before it was cool, because like shortly after, a few months after we did this and implemented this, some malware, I forgot the name, basically also had like an embedded disassembler. So we were doing it before it was cool. Now it's cringe. On a more serious note, how do we do the state extraction in interpreter mode? Basically, we first run the optimized execution, know which bytecode offsets we are interested in, and then hook these bytecode instructions, which is just happens by like every bytecode instruction has an handler which ends up calling dispatch, and in this dispatch we call our dumpling hook, which then like just parses the C++ object, which is the bytecode handler, which is the VM state. Well, not exactly C++, not exactly everything here is like C++, because just also another interesting fact that's not quite important for our approach, but these bytecode handlers are actually not directly written in C++, but they're written in like a kind of macro assembly, which is then not compiled by Clang, but during the build process of the engine, they are like optimized by Tryptophan for some reason. So probably they noticed it was faster to do it that way, so that they're like the handlers itself are straight lowered to assembly basically. Sparkplug is another interesting case. Sparkplug is basically an unoptimized JIT compiler, which also just basically directly takes bytecode instructions and lowers them to machine code. So Sparkplug we can treat very similar to the interpreter in terms of inserting our hook in our hook during code gen, and then also doing the dumping in a way, in the basically the same way we did in the interpreter. Okay, and by the way, Maglev is pretty much the same as Tryptophan. We end up using basically the same code for it. Okay, so now that we have these basically C++ objects that are the VM state, we implement a like robust, invariant, and still fine-grained and in-depth way of dumping this VM state, meaning serializing all the objects with all the details that need to be invariant across execution tiers. And this is actually not the format that we use, but we have a more minimized format. This one is just for readability, but it contains like all this information about, as you can see here, we notice we notice even like small discrepancies, small details of the VM state, like -0, infinity, and properties of an object, and all that. Maybe like a few words on the minimization. Basically, we just store the thing that changed compared to the last dumped state, and use shorter values than the string values here. Let's talk a bit about the matching frames together, which sounds like a very straightforward and obvious thing to implement, but there is one very subtle challenge that ends up having a nice solution, but it's at least worth to think about it and talk about it a bit. Maybe I made it seem that the optimization continues like at the exact same point of in the function where the JIT left off in the interpreter. This is not quite possible, but it can go back like a small amount of bytecode instructions before that, basically, right? Just as and this can be rather annoying because like in this case, going back, like the JIT was here on the shift, and then it goes back to the same instructions, like just a regular de-optimization. But a de-optimization can like also be inside a loop, which in itself is not a problem, but in combination with jumping out of loops, like here, this example, this toy example basically jumps out of the loop. So there is not a one-to-one mapping of dumps anymore. But just the fact that the VM state is the whole state of the program, and we're like a fuzz case by definition terminated. So the fuzz case never had a repeated value of the VM state, because the VM state is the whole state of the program. So it ended up being enough to just check all the JIT dumps and see if they have an dump in the same function invocation. Yeah. Okay. We're not the first people to do differential JS engine fuzzing between execution tiers. So let's have a few words about the state of the art. You could use it. You could say it in a rather mean way. It's a bit more complex than that. But what they like, what it comes down to doing is they insert the equivalent of console log statements of variables in the program. So they change the input program, which has the problem of modifying the program. Modifying the program has the problem of inhibiting JIT compilation, basically. Let's talk about this in more detail. One paper that does differential fuzzing between JIT execution tiers is FuzzJIT. They run just like they construct a JavaScript program, which so they don't do two executions, but they do one execution of the same program where they have a function and compare the output value of it first, like without where the JIT compiler wasn't run yet. Then they call the function a bunch of times to trigger JIT compilation, and then they see if the function still does the same with like a deep equals comparison. Yeah, this approach is like very susceptible to false positives, and that's why they write we disable the generation of complex statements such as function declaration, class declaration, try-catch statements, switch statements. We also avoid generating loop structures inside the function body of opt. So yeah, they're not very thoroughly testing the JIT engine, but still very nice approach. What is not so nice is that what they write in the paper obviously doesn't correspond to what is in their released artifact. Like, this is not something they ever do. The code, like this is an example that the artifact basically generates. It has also a lot of false positives, despite all the efforts to reduce them. And we, and more systematically, some previous work, are just unable to reproduce their coverage results for some reason. Yeah. Also, like on a more theoretical level, apart from the implementation, this approach of calling basically opt with like a static parameter the whole time isn't exercising JIT optimizations very well, because for exercising JIT optimizations well, you need to have like a diverse set of input values to the JIT compiled function, such that it will do interesting assumptions basically. Yeah. There's another paper that does differential fuzzing between execution tiers called JITpicker. What they do is they insert these probes called probe states in the paper with a very small probability, and then probe one variable. And yeah, this approach is successful, but has the problem that the very probe itself is like a sink in the program, so it can it will influence and reduce basically optimizations applied by optimizing JIT compilers. Another shortcoming of the paper is that like every object, like they don't go in depth into objects, at least for the V8 implementation I looked at. Like all objects are basically equal to each other. If you want to, like, what they do is they accumulate a hash. So it's not like a console log, but they accumulate a hash over the values that they probed with low probability. In terms of evaluation, we run we run dumpling against the state of the art in differential fuzzing, and also against Fuzzly, the non-differential fuzzer, that all the differential fuzzers build upon. And of course, our approach of fine-grained dumping will be slower, but we're surprised that it's not that much slower if you compare coverage over time. We're still competitive, also in terms of executions. We're still competitive, even though we do this extensive bug oracle. We find, in our evaluation, we find 8 new V8 bugs. Also ones that in the evaluation runs the competitive fuzzers didn't find. Notably, Chitpicker found 2 of them. Yeah. To give you one example of a bug that Dumpling found, we have function A that the details of the bug are not that relevant, but just to see what's going on here, it sets like writable and configurable properties of a member of this A. Just in JavaScript, functions are also objects, and with just this small snippet of JavaScript, Dumpling is already able to spot a differential where the interpreter differs from JIT compilers, whereas other fuzzers would need to generate something to probe the broken state. The bug was basically that X wasn't marked as enumerable. In this case, it was actually an interpreter bug. So we have the advantage of, you could say, catching bugs earlier, not having to manually probe the state in terms of inserting a console log or a probe state statement here. As a conclusion, the key problem we wanted to solve with Dumpling is to find differentials between JavaScript execution tiers automatically at scale. And we do this by extracting the states at runtime and comparing them between the JIT and the interpreter, leveraging, and implementation-wise, we leverage something, specifically the optimization points. That is a mechanism that's already implemented in the fuzz target, in this case the JS engine, and we believe that these basically tailored bug oracle to the fuzz target targets are successful and a viable approach for important critical targets such as JavaScript engines are. And as a result, you could say we find bugs before they become visible. Thank you for the attention. I guess this is a YouTube video, so you can leave questions in the comments. You can find our artifact, the code of Dumpling here, and you can also contact me for any questions. Thank you.